Okay, so when we vibrate to DML, as we've mentioned, we'll take an exciter, this transducer, and we attach it to the DML, like so. And there are certain locations that we would attach the exciter that give us a more optimized response. And we can also attach multiple exciters. That can give us more power handling. And also multiple exciters can also give us a smoother response as well. So
yeah, what about extending response? Will the addition of more exciters actually extend the frequency response, or help you find exactly what kind of optimal bandwidth or operating bandpass the loudspeaker can work at?
Yeah, absolutely. I mean, you want to keep the exciters as fairly close together as possible, because at the very higher frequencies you're going to get some interactions, and the closer they are, the smoother your power response will be.
Are those interactions a function of the distance between each other and also the size of the coil? Has something to do with
it? They are. Those interactions are to do with the spacing of the exciters from each other, causing because there will be some interference effects in distance, but also the diameter of the voice coil is, as you say, is a very key component of this, how it operates.
The fact that the panel itself has very different ways of generating audio or generating, I guess, sound at different frequencies, that it doesn't work like a piston, and that it has a set of very, very different behaviors. And that's actually what kind of makes me super interested in it, because I can pretty much predict the behavior of a cone in a conventional device. You know, based on the material of the cone, the stiffness of the cone, the material, the size, the weight, the speed, and then of course, you know, adding some other standard calculations for speed of sound and diameter of the cone, etc. But this actually behaves quite differently.
Yes. Yeah. I mean, this is what's known as a dispersive object, which means its wave speed varies with frequency. So we're very familiar with the wave speed in air being constant with frequency. So whether it's a high frequency or a low frequency, generally it travels at the same speed. In a panel, a low frequency wave, bending wave, travels at a different speed from a high frequency wave. And that introduces some very unique properties. One of which is that we talk about this primary radiation zone that occurs when an exciter drives force into the panel, energy into the panel. A region around the exciter is initially excited, initially driven, and the size of that depends upon the frequency that you're driving in. And so at higher frequencies, that region reduces in size. And so the panel automatically adjusts its initial radiation zone to compensate, to give you wide bandwidth, even at high frequencies, from an object this size. And this is the size of, a couple of few 12-inch drive units.
Right. But
we can generate, very high frequencies from this object, and over a wide bandwidth as well.
So it's actually breaking up.
It's intentionally, we're breaking this up, intentionally. But we're doing it in a very controlled way. And I think when you look at a cone speaker, the stiffness in a cone is generally achieved through its geometry. Because, for example, paper is a typical material, thin paper, and it's not very stiff. When you form it into a cone shape, it becomes very stiff. And as you drive energy in, generally when the wavelength is long at lower frequencies, the energy travels through as a uniform, single. There's no time delay so much, and so it doesn't break up. But once the wavelength of the energy going in, or the vibrations going in, becomes comparable to the size, then the cone starts to buckle. And it's very simple. If you take a cone of paper and you push down on it, it's quite stiff. But the moment you just touch the side, the whole thing collapses. And that's kind of a bit like breakup in a cone. And when it happens, generally it's not so well controlled. And that's why it sounds bad and why you have to use a tweeter.
It also not only sounds bad, it becomes very audible. Because it's a breakup mode that is unpleasant, usually creating some odd harmonics.
Yeah.
Okay.
And what we find here is that we intentionally break it up, but we control those breakups through the material properties, the damping, the boundary conditions, the exciter even, and that gives us a very smooth, sweet sound.